The next best practice comes from Ashish Mohite. I hope I pronounce it the right way. And he's an architect and PhD researcher at Aalto University in Finland. And he is the co-founder and chief design officer of Hyperion Robotics. So you pursue the same vision as, I might say, most of the best practice examples we're going to see. You want to make the construction industry more sustainable and more efficient. And you work with concrete, but a special mix of concrete. But I don't want to spoil it, so I'm going to give it to you. Ashish, we're very happy to have you with us, and show us what your contribution to a more sustainable construction industry is.
Hi, thank you for inviting me. So I'm from Hyperion Robotics, and as you can hear and see, that Hyperion Robotics is based in Finland, from my voice, and we are leading the transition to sustainable automated construction. Created for the builders of tomorrow, our solution will save and upcycle, optimize for today. So concrete is, as you know, is the second most used material on the planet, and construction industry is the most material intensive industry in the world. 42 billion tons of material is used by construction industry annually, and responsible for 1/3 of the global waste. Cement is one of the biggest culprit, right? Because cement is one of the most used material on the planet, and cement production actually contributes to 8% of the global CO2, and 30% of the electricity produced in the EU is just used for cement production. So those numbers are really, really high. And the second constituent of the concrete is sand. Sand is the most mined material on the planet. We consume roughly 40 to 50 billion tons of sand annually. That's equivalent to one person consuming 6.5 tons of sand, which is like more than a weight of an elephant. How can we make a construction industry sustainable? How can we reduce the carbon footprint? How can we reduce the CO2 emission? But there is a solution. So the solution is in the waste. As humans, we produce a lot of waste, and only fraction of the waste gets used. So just put that in numbers, is 282 billion tons of waste we have on our planet. 27% of the total EU waste is mining tailings, so waste material from the mining industry. 18% comes from the paper manufacturing, and 900 million tons comes from construction waste. Some of the construction waste gets used, but if we want to achieve our targets of CO2 emission, we need to use more than 70%. We have 2 billion tons. We produce 2 billion tons of waste in Europe every year, and that's alarming. And that comes to the question of recycling. So there is a huge opportunity to recycle this 2 billion tons of waste. And there comes 3D printing. So one of the ways through which we can solve this problem is through automation. And in automation, specifically, we do concrete 3D printing. So 3D printing of concrete reinforced. So this is one of the structures which we 3D printed. We set up this kind of 3D printing micro factories. So basically, we set up these micro factories where we take our robotic arm and the material mixer and the pump, and we go on site, and then we print those objects which are to be printed on site. I will explain one of the use cases, which is the pad foundation, which we have 3D printed recently. This is on the left-hand side. You see, this is how the pad foundations are done currently. So they just go on the side, they cast like a cube of concrete, and we, by doing optimized geometry, could actually reduce 75% less material than the traditional way. And this is where the power of 3D printing comes into picture. That 3D printing is, as everybody knows, that you add only a material where it's required, and you can optimize the geometry to reduce the material use. So we are only using 25% of the total material now. So that means a lot of material savings. That means a lot of CO2 savings. We have also developed a specific software for that. So this software doesn't work like any kind of a typical 3D printing slicing software. This works specifically for these kind of optimized objects. So here one customer can put loads of structural loads of what the object is gonna have, and then depending on that, robotic toolpath directly gets generated. And then the customer just has to print, and the object gets printed. We also have in the back end, the design for additive manufacturing is going on. So in that back end, there is an FEM analysis going on, which optimizes the geometry the best way it can be optimized for both for structural reasons and for 3D printing, to make an optimized toolpath for 3D printing. And this is the example. So this is actually, of course, reinforced. So there is steel structure inside. We also have automated way of how to place the reinforcement bars. And then those objects get shipped on the site with a truck, and that get installed. And then testing. So testing is one of the most important part in order for the 3D printed parts to be accepted into the industry. We already have that done for metal additive manufacturing, but concrete manufacturing, concrete 3D printing is fairly new. So we have to always prove that our objects work structurally. And for that same reason, we are also part of a ISO committee, which is coming up with a new ISO standard for 3D printing in construction sector, because we already have ISO standards for 3D printing for other sectors, but doesn't exist for the construction sector. And the most important part is materials. So I believe, and what we believe, is that the material is the key. On any kind of 3D printing, material is the key, but specifically in concrete 3D printing, we have developed materials using waste materials. So this is why I had slides in the beginning which talked about the worldwide waste and what kind of waste we produce. And most of this waste can actually use and reuse to create this kind of new material, because 3D printing gives us a new opportunity to use new materials. And we have developed a material which is 97% recycled. And the carbon footprint, the CO2 footprint of this material is 15 kilograms per ton. We have a large network. We work with large companies, also research institutions. So we also work with Fraunhofer Institute. We also 3D printed some artificial reefs, which were installed in Rostock in Germany in the Baltic Sea. And we recently got also funding from Sprint D, which is a German government instrument to decarbonization. There was a call specifically for that. So we are looking forward to work on that project. Thank you very much.